Okay, welcome everyone. Welcome to this regular seminar of the cost action on relativistic quantum information. So this seminar is the one of Working Group 1, which is devoted to studying problems in quantum information aspects of quantum field theory. And I will pass to Vilasini, who is going to introduce our speaker today.
Thank you, Kasia. So yeah, welcome everyone. And it's really my pleasure to welcome Alex May today for our second seminar of this series. Alex is currently a junior professor at the Perimeter Institute of Theoretical Studies. And I think he has a lot of interesting work at that spans the interface of quantum information and quantum gravity. And quite a few questions that are might be of really direct interest to our working group. So we're really happy to have him here for the seminar. And so without further ado, Alex, please feel free to get started whenever you.
Great. Yeah, so thanks for the introduction and thanks for the invitation to speak. I think it's a great talk for me, or great group for me to be giving a talk to, because I think it's a group that I have a lot of natural overlap with, but haven't really interacted a lot with before. So I'm excited to get that started. So I'm going to be speaking about some aspects of quantum information that are relevant to or most apparent in the context of causality or causality constraints, and how those connect to quantum gravity. Okay. So I'm going to be taking a sort of simple or kind of practical view of quantum information in a spacetime context. I'm going to describe that next. I want to go through it sort of slowly because I think while it's kind of simple, I think it's maybe slightly different than the perspective taken by other approaches to this subject. Yeah, so we're going to go through that. And then I want to highlight or try and explain how this perspective on quantum information in spacetime can give us some insight into some of the basic questions in quantum gravity. Okay, and in particular, to try and organize ourselves, I've sort of highlighted two basic questions about quantum gravity. The first is about holography, or what's called the holographic principle. So if you're not familiar with this already, this is the statement that, or the claim that gravity in, say, d+1 dimensions should have some alternative lower dimensional description in terms of just a quantum mechanical theory which lives in just d dimensions. And yeah, we're going to explore that. And then the second point that I want to explore is another basic question about quantum gravity, which is just how do we take some gravitational degrees of freedom, in particular the metric degree of freedom, and record it into some quantum mechanical sort of framework. Okay. Good. So let me start with my sort of perspective on quantum information in spacetime. So to introduce this, let me first of all contrast it with sort of the usual scenario in quantum information processing. So typically, if we had some kind of quantum information processing task, we would specify, there's some sort of inputs that I'm given, maybe a quantum state on some Hilbert spaces X and Y, and then I'm required to transform them in some way, and then return as an output some transform state, say U acting on psi. Okay. And for convenience, linguistically, I'm going to think about some sort of referee who's giving you these inputs, and then you're doing this transformation, and then you're returning to the referee these outputs. And then the referee is going to perform some sort of check on the output that he's given to see if you've completed this task. And you might assign some success probability to how well or how closely you've done this task. Okay. So that's something like the usual scenario. And then when we start thinking about a spacetime context, we're going to change this or upgrade this sort of slightly. We're going to need to keep track in the spacetime context of where in spacetime the inputs are given to me and where in spacetime I need to return the outputs. So to keep track of that, I'm going to draw pictures like this, where these are spacetime diagrams. I have some set of input points, which I'm going to label C with some index. At each input point, I'm given some system, which is part of my input, say X here, and then at C1, Y here. I need to transform those in some way that's specified, and then return the outputs at some other set of spacetime locations. So this kind of picture, or this kind of framework for thinking about things, is something that was emphasized by Adrian Kent back in 2012, and actually has been explored further by Emily, who was the speaker last week, I guess, or at the last seminar. Okay, so an important point, which will probably be obvious to this audience, is that in this context, causal relationships are very important. So for instance, I'm drawing here two different relativistic quantum tasks, which have the same inputs and outputs. So for illustration, I'm going to choose a sort of trivial one where I'm just given some unknown quantum state and asked to return that state at some other point. For that task, it's important, or it's relevant, what the causal relationship of the input and output points is. Okay, so in this picture on the left, I'm given X at some location C0. I'm supposed to return X at some other location R0, which is in the future light cone of C0. And in that context, it's very easy to complete this task. We can imagine recording it into some degrees of freedom, some photon or something like this, and sending it between the locations. And at least in principle, I can complete this task well. On the other hand, if these points are causally separated, they're space-like separated, then this task becomes very hard, and you won't be able to complete it very well. So this causal relationship is appearing in this number, the success probability for completing the task. Okay, so beyond these kind of point-to-point causal relationships, whether each output is in the future of each input, there's further sort of more subtle aspects of causal structure that can be relevant for completing these tasks. So for example, here I've illustrated two situations, which both have the property that all of the output points are in the future of all of the input points. Okay, so that's what I'm writing down here. And this is just saying that if I look at C0, I can get to R0, and I can get to R1. And if I look at C1, I can get to R1, and I can get to R0. And that's true in both cases. Okay. But the causal structure of these two situations, these two tasks, is nonetheless different. They're just different in a slightly more subtle way. So in particular, on the left, there's some region here in the middle, which is in the future of C0 and the future of C1, and simultaneously in the past of R0 and the past of R1. Okay, so causally, this means I could bring systems from C0 and C1 together inside of this region, maybe interact them in some way, and then pull them apart again and get them out to the outputs. Okay. In contrast, in the situation on the right, though I still have these sort of basic causal relationships among the input and output points, I don't have this region sort of in the middle of all four of them. Okay. And okay, you can sort of convince yourself of that carefully if you drew all the light cones, but maybe operationally what this means is if I try and get together between C0 and C1 in some way, I will always be sort of too late to get to one of the output points. Okay. So this kind of more refined statement about the causal structure also has implications for completing causal tasks or completing quantum tasks in this setting. So to illustrate that, let me take a really simple example. So let's say over at C0, I'm given an unknown quantum state psi, and then at C1, I'm given a bit b, which is either 0 or 1. And then the goal is to bring psi to r sub b. So if b is 0, bring psi over here. And if r is 1, bring psi over here. Or b is 1, bring psi over there. So in the situation on the left, this is very easy to do, right? I would just take psi into the middle. I would look at b, and then I would redirect psi based on the value of b. Okay, so that's fine. But on the right, that same strategy is not available to me, right? So that strategy relied on the existence of this geometrical region, this scattering region. But that's not available on the right, so it's now unclear whether or not I can complete this task. I claim, though, that actually you can complete the task in the situation on the right. You just have to add in an extra ingredient, which is entanglement. Okay, so in particular, let's think about sharing some maximally entangled state between C0 and C1. So that's my squiggly line here. It's a state on Y and Z. And then actually by exploiting the teleportation protocol, we can complete this task even though we don't have the scattering region. So to do that, we would, first of all, take the state psi on X that appears at C0. We would measure it along with Y in the Bell basis, as if we're doing teleportation. We'll get some measurement outcome M. That's classical, so we can copy it, and we're going to send it to both R0 and R1. Okay. And then meanwhile, over near C1, I hold this quantum system Z. The quantum system Z is needed to recover the state psi. So I have to send it to the right place. But fortunately, Z is now located at the same place as B. And so we can look at B and decide to send Z either to R0 or R1 based on the value of B. Okay. And then once I do that, let's say that B was 0, I would take Z over to R0. I would have Z and M at R0. And from that, we know we can recover psi. Okay. So coming back to the two pictures, on the left, we saw that we could complete this task by using this scattering region or this geometrical sort of object. And on the right, we can complete the same task, but in a different way and using entanglement. Okay. And this illustrates, I think, a very general and important feature of quantum information in the context of spacetime, which is that aspects of geometry, and in particular causal structures, right? Like for instance, the scattering region, can sort of be interchangeable resources with entanglement. Okay, so entanglement and this causal feature operationally are letting you do the same thing. Okay, and we're going to see this basic lesson from quantum information in a space-time context reappear when we look at quantum gravity. I'll also say it's okay to interrupt me with questions along the way. Okay, so now let's get into the quantum gravity side of things. So we're specifically going to be thinking about quantum gravity in the context of the AdS CFT correspondence. So I'm not assuming that you know anything about AdS CFT, so let me give you my sort of potted quick introduction to what AdS CFT is. So AdS CFT is a conjectured equivalence of two apparently very different looking physical theories. On one side of the equivalence is a theory of quantum gravity that lives in a special kind of a space-time called an asymptotically AdS space. Okay, so that's what I'm drawing here as this cylinder. Okay. On the other side of the equivalence is a special kind of a field theory called a conformal field theory. And that field theory lives at the boundary of this AdS space. Okay, so this rectangle I'm drawing on the right, you should think of as the boundary of the cylinder that I've sliced open somewhere and rolled out flat on the page. So in particular, the two sides of my rectangle are identified. Okay, so a couple of points that I want to emphasize about AdS CFT. First, and it's sort of apparent from the pictures, but it's worth emphasizing, is that this theory of quantum gravity lives in one more dimension than the conformal field theory, right? And that's sort of strange. You know, how can theories with different dimensions be equivalent? But it's actually a general feature of quantum gravity that we expect on general arguments to do having to do with black holes. So there's a sort of more general principle, the holographic principle, which is something we think is true or has been argued to be true for theories of quantum gravity broadly. And you should think of AdS CFT as one manifestation or realization of that general principle. Okay. The other comment that I want to emphasize is that this theory of quantum gravity living in the AdS space, there's some regime where it's described by classical gravity or quantum field theory on a classical gravity sort of background. That's the regime we're going to be most interested in. One thing that means is that within this AdS theory, there is all of this sort of physics of classical gravity that you're familiar with and you know and love. So, you know, in your AdS space, you could have planets orbiting around stars, or you could have black holes forming, or you can have gravity waves propagating, and so on. And all of that physics is somehow written into or recorded into this quantum mechanical theory, the conformal field theory. Okay. In particular, the theory of classical gravity is a theory of, you know, a dynamical geometry. So there's some metric degree of freedom, and this is dynamical. It's governed by some equation of motion, Einstein's equation, and somehow that dynamics is written into the CFT. And this is true despite the fact that the CFT, which lives at the boundary, lives on a fixed spacetime background. So the metric over that the CFT lives on would just be some fixed Minkowski space sort of metric. And so it doesn't have a dynamical geometry, but it's somehow in its quantum mechanical degrees of freedom recording the dynamics of this metric. Okay. Yeah, so we're very interested in understanding, you know, how does that work? How does that happen in AdS CFT? Okay. Okay, so a couple of points about a couple of further points about AdS CFT. It's conjectured to be a sort of complete theory of quantum gravity, meaning that it's conjectured to be valid at all energy scales. That's great and exciting and interesting to explore. The limitation to keep in mind, of course, is that if we look out into the universe, it doesn't seem that we live in an asymptotically AdS space. And so the way you can think of this is AdS CFT is sort of a theory of quantum gravity, but it's not kind of the theory of quantum gravity that describes the world that we live in, right? Still, it's some, you know, in principle realization of a lot of the features of quantum gravity that we expect to happen, you know, in a theory of gravity that describes our world. So it's worth studying, worth understanding sort of key lessons from AdS CFT, how they work, and hopefully extracting those key lessons and using them in developing a theory of quantum gravity that applies to, you know, the actual world. Okay. And then, as I mentioned earlier, we're going to be trying to do that, trying to understand some of the key features of AdS CFT from this quantum information kind of perspective. And we're going to focus on those two points that I made earlier about, you know, how does this holographic principle work? And then how are these metric or gravitational degrees of freedom written into the quantum mechanical theory? Yeah, raised hand, go for it.
Yeah, so just a short question about these points. I mean, I'm wondering, some people actually consider that you can actually use AdS CFT as a way of defining your theory of quantum gravity in the regime where quantum effects in your space-time are non-trivial. So in principle, one could hope that maybe in that way one can also learn something about quantum gravity in the non-trivial regime. Could one regard that as a sort of additional separate point to these two A and B that you mentioned here?
Yeah, so, okay, so yeah, maybe let me first comment that, right, so we think that kind of comes back to this first point I made. It's conjectured to be a complete theory of quantum gravity at all energy scales, right? So, and there's kind of two ways to think about that. So you can say the bulk, the AdS theory, I'm going to define it in terms of string theory, okay? And then I'm going to conjecture that that string theory is dual to or equivalent to this CFT, and then that holds at all energy scales. That's one perspective you can take. Or you can say, okay, I can look at the sort of low energy semi-classical regime of the bulk, verify pretty well that that's equivalent to the CFT, and then say, I'm going to define the high energy description of the bulk, the complete description of the bulk, in terms of the CFT, right? And so then this thing's sort of more tautologically true or something, but you just don't know what the bulk exactly looks like. You're just saying it's described by the CFT. Those are both good perspectives. Yeah. Right. And then your other point, right, was then that, yeah, you can try and, so, okay, my points A and B are both focused on sort of the semi-classical regime. So they're saying, they're about how do we get this sort of higher dimensional gravity theory, like described by GR or QFT on a curved background. How do we fit that into the CFT? That's the question I'm most interested in. But you can also say, oh, I want to explore stringy physics. I want to explore high energy physics. How was that written into the CFT? And those are good questions that I'm not exploring here.
Okay, thank you.
Yeah, so slightly long-winded answer, but interesting question. Okay, I'll keep going unless there's other questions. Okay, good. So that's my kind of lightning introduction to AdS CFT. Fortunately for this talk, you don't need to know a lot about it. Really just the pictures are going to be enough to give you a sense of what I'm saying, or a good sense of what I'm saying. Okay, so to address these points about AdS CFT, at this point A and B, I want to bring this kind of relativistic quantum task perspective to bear on this duality, or to bear on AdS CFT. Okay, and here's how we're going to do that. So let's start with the bulk or AdS gravity picture, and let's think about these relativistic quantum information processing tasks in that setting. Okay, so I'm going to define in my AdS space some input points, these C's, and some output points, and think about some some inputs and outputs, or completing some tasks with those inputs and output points. Okay. I can do that, and furthermore, I could think about every such task that I could define in the AdS space, and I would associate with each task some success probability of completing it. Okay. That would be some huge list of a bunch of different tasks and their success probabilities. And that big list is going to capture a bunch of data about the gravity side of this duality, about the AdS quantum gravity theory. Okay. And then I could repeat that sort of procedure for the CFT. So I could think of every task that I can define in the CFT, and let's call them T hat I, and their associated success probabilities. And that's some big, huge list that captures a bunch of data about the CFT. Okay. And then the claim of AdS CFT is that these two theories are equivalent in some sense. Okay. And if that's true, then we would think that these two big lists that capture a bunch of data about their respective theories should be in some sort of correspondence. Okay. The data in these two lists should match up in some way. The way that we're going to make sense of that, or make that claim more precise, is we're first of all going to restrict our attention to thinking about tasks in the bulk perspective, in the AdS perspective, where the inputs and outputs are off at spatial infinity. Okay, so I haven't described this in detail, but in this sort of cylinder picture of AdS, the points at the boundary are infinitely far away spatially. And formally, points at the boundary are actually identified with light rays that go off in some direction. Okay, so I'm going to restrict myself to thinking about tasks where my input systems are coming in from some light-like direction from the boundary, and then my outputs are going out, along some other null line out to the boundary again. Okay. For those tasks where the inputs and outputs sort of occur at infinity, I can make sense of some sort of dual corresponding task in the CFT, right? So this point C0, where I have an input, becomes this point C0, where I have an input in the CFT. Okay, so with that kind of procedure, I understand what it means to have a given bulk task and then some corresponding boundary tasks T hat. Okay. Once I've done that, once I have a procedure for identifying a bulk and boundary task, the correspondence or the equivalence of these two theories, one thing that it tells me is that the success probabilities for those tasks, which is some number, should be the same. They should match up. Okay. So this is, some way of capturing the fact that these two theories are equivalent, and it's capturing it in a very sort of operational quantum information theorist sort of a language. This is from a traditional AdS CFT sort of perspective, or from a high energy physics sort of perspective, this is a really weird way to think about the correspondence. But I claim that this perspective, which highlights, quantum information, and in particular quantum information processing in a causal kind of context, brings out certain features of the correspondence that are very hard to see otherwise. It's very hard to see from a more standard high energy physicist sort of perspective. So we're going to get some new insight into the correspondence by taking this perspective. Okay, so that's going to be our general sort of framework for thinking about this. Let me now try and address, these 2 points A and B, about the correspondence from this perspective. Okay. So recall that the first point was about the holographic principle. We wanted to understand, how can I have a higher dimensional theory written into a lower dimensional one? To better understand that, I first want to sort of sharpen the question into a kind of concrete puzzle. Okay. So here's the puzzle. We're going to think about a relativistic quantum task that looks like this thing on the left. So I'm given 2 quantum systems, A0 and A1, at C0 and C1. They're going to come in from infinity towards the center of the AdS space. And then I want to return those systems at R0 and R1. And in the meantime, they should have transformed under some unitary U. Okay. And then because these inputs and outputs happen in infinity, I can make sense of the same task from the boundary perspective. Okay, so I'm going to focus on a task like that. And then I'm going to specifically choose my points C0, C1, R0, R1, such that in the bulk geometry, it's possible to bring these systems together and interact them locally, and then bring them out again to the boundary. Or in other words, in the language I was using earlier, this task sort of has a scattering region in this bulk perspective. Okay. The puzzle, though, is that I claim there is no such scattering region in the boundary perspective. Okay, so to see that, let's look at the causal structure in the boundary. I've started here by drawing the future light cones of C0 and C1. So those are coming up like this, and then like this. And then here's the backward light cones of R0 and R1. And then what's interesting is that there's no overlap of all 4 light cones. So there's no scattering region in the boundary. To see that more explicitly, you could say, well, if I tried to meet up between C0 and C1, I could meet somewhere like this. I can get a signal out to R0, but now not to R1. And similarly, I could meet over here, right at P1, and now I can get out to R1, but not to R0. So there's no point that lets me meet and get to both. Okay. So the puzzle then is, in the bulk perspective, we can have this local interaction occur. But in the boundary, we know that the same process should happen, that interaction has to occur, but there's no place for the interaction to happen, right? So this is sort of strange. When you think about that, it seems hard for the CFT to reproduce the higher dimensional physics of the bulk theory. So maybe this is confusing. We might ask, did we misunderstand something? But it will turn out, and I've already sort of set it up or hinted at it, that quantum information in a spacetime context and results that are known there will let us understand this. Okay. So to get there, I want to go on a little bit of a detour to a subject in cryptography known as position verification. So let me introduce that. Let me introduce that. So the position verification scenario is played by two players. So there's Alice and Bob, and the goal is for Bob to verify Alice's location in space while only talking to her remotely. Okay, so as a sort of cartoon, we could imagine the situation on the right here. We have Bob, who has two labs. Say he has a lab in Oahu and a lab on the Big Island. And Alice, meanwhile, is supposed to be in her lab on the island of Maui. Okay, to try and verify this, what Bob is going to do is he's going to send Alice some signals, right? Ask Alice to maybe compute something from those signals and send him something back. And if Alice responds with the correct output and at the correct time, then Bob is going to trust that Alice is where she claims she is. Okay. This is the general idea. Okay, so in a space-time picture, as opposed to a sort of cartoon picture, the setup looks like this. So we have Bob over here in his lab, another agent of Bob over here in his lab. Alice is supposed to be in this box in the middle, right? And then Bob is going to send in these signals. Alice is supposed to do some, say unitary on these signals, and then return the outputs. Okay. So if Alice is being honest, that's what she's going to do. She's going to be in the middle. She's going to do the unitary as she's supposed to. On the other hand, if Alice is going to cheat, she can use the following sort of strategy. So she can have an agent, these two people with black hats, not on the island like they're supposed to be, or not in the region where they're supposed to be, but sitting on either side of it. And they are going to intercept the signals that are coming in, A0 and A1. They can act on those inputs in some general way. Okay, those are my yellow dots. They keep some system, they send some system across. They act again at the end, and then they give some outputs, A0 and A1 to R0 and R1. And hopefully, if they've succeeded in cheating, this overall process looks the same as the process that would have happened had Alice acted in the middle. Okay. So then the question that was asked in the cryptography literature is just, is there some choice of unitary that I can ask Alice to do, which forces her to act honestly, right? Is there some unitaries which can only act or can only be implemented by bringing everything together and acting locally, or can everything be realized in this kind of cheating or what we'll call the non-local form? Okay. And then a key result or key insight from the cryptography literature here is that actually for all unitaries, and more generally all quantum channels, there is a way to implement it in this sort of non-local or cheating form. But to do so, you need to share some entanglement between the left and the right. Okay, so these operations here and here need to also take in some shared entangled system. Okay. So that insight is going to help us understand this puzzle in AdS CFT. So to do that, let me kind of put all four pictures here together. So we have the bulk and boundary pictures in AdS CFT, and then the honest and cheating pictures in the position verification scenario. Let's start with the bulk AdS picture. So we said that there, these quantum systems can be brought together and interacted locally. That looks like the honest picture in the position verification scenario, right? Again, those systems are brought together and interacted locally. And then we learned from the cryptographic results that local interaction can be re-expressed or sort of simulated in this other non-local or cheating form. Okay. And I claim that the way that AdS CFT is reproducing this local interaction in the boundary CFT picture is via a similar sort of process. Okay, so in particular, while in the boundary we don't have some place, some single location where the interaction can happen, we do have something like this. So say in the future of C1, we could take the output there or the input there and act with some general quantum operation here. Similarly, near C0, we could do some quantum operation, and then we can send signals towards R0 and R1. We could act locally again in those two locations, and then give some output, and hopefully by doing this, reproduce this local unitary. And then the observation is just that process that's happening or that can happen in the CFT in the boundary actually has the exact same causal structure as the cheating strategy in this position verification scenario. So this graph of causal connections in the boundary is the same one as the graph of causal connections in the cheating scenario. To highlight that, I've given labels to the vertices in the graph. So you can think of say this vertex here 1, which connects to 3 and connects to 4. If I look at this picture up here, also that vertex 1 connects to 3 and connects to 4, and then similarly 2 connects to 3 and 2 connects to 4. So these are the same picture, the same graph. They're just laid out in the page in a slightly different way. Okay. Good. So the insight then is that we can resolve this earlier puzzle. We can understand how these local interactions in the bulk AdS space get reproduced in the lower dimensional boundary theory. And how they're getting reproduced is via one of these non-local interactions or non-local computations. And further, because from the cryptographic side, they'd understood that entanglement was necessary to do that, to reproduce these interactions. We also understand that somehow entanglement must be playing some important role in the CFT to let these interactions be reproduced. Yeah, Albert.
Yes, so the explanation was very clear, but just a question which is slightly related to my earlier question, in the sense that, I mean, one can take this more general view of AdS CFT, but if you focus in the regime where, as far as I understood correctly, if I understood correctly, all the fields propagating in the bulk are classical, right? Are we in that regime?
We're actually in a regime, sorry, maybe I should have specified this a bit clearer. So we're in a regime in the bulk where we have a well-defined geometry. So I can talk about light cones and light rays and things in the bulk. But I do have quantum fields sitting on top of that geometry. So like I can still think about this sort of thought experiment in the bulk where I have some quantum systems, A0, A1, propagating in and interacting somewhere and then coming out again.
Okay, because that was my question. But then that regime in AdS CFT, these fields that are quantum in the bulk, those would still be like some stringy excitations. So
Yeah, in principle, we would think that though, like that the bulk is ultimately described by some string theory, and there would be some way of understanding, that description, which is sort of QFT on a curved background. There'd be some way of understanding that from some, from some stringy perspective. But we don't have to do that right now. We're just saying, it's well described by sort of QFT on a curved background, and we're going to think about this process happening from that perspective.
Yeah, I agree. It's just that I think that you are probing actually a little bit that regime that we were saying. I mean, not the large space-time fluctuations, but in some sense, not that I remember very, very well in detail, but in this expansion of 1/n that you can have in the CFT, and then you can have the connection with that in the bulk. I think that, if I understand correctly, you are going beyond the leading order in 1/n, which would be really purely semi-classical. Everything would be classical fields in the bulk. And I think that you are starting to explore in some sense implicitly some already corrections to next, at least beyond that leading order in 1/n. I mean, that's not necessary to get into the details for you, but it's just for me to point out that it seems to me that you're exploring already some quantum aspects in the bulk, maybe not in the large quantum gravity regime, but already some non-trivial fluctuation.
No, that's right. So, but I would say, like, already when I say QFT on a curved background, that's sort of already beyond leading order in 1/n, because it's there's like there's sort of the purely geometrical part, which is like in some sense in this expansion the kind of leading part, and then there's like the quantum fields sitting on top of the geometry, and those are kind of the next term.
Yeah, but I think then maybe it's a matter of a little bit terminology for people from other communities, like some of the people I had worked with in earlier days when people were talking about quantum field theory in curved space-time, not in connection with AdS CFT. That really meant that you had a fixed background space-time curve, and the thing that you were quantizing were test quantum fields. But to put it in a more explicitly, gravitons were not taken into account. Whereas it seems to me that here, okay, it's stringy, it's a string field theory. Sorry, it's a string theory in the box, so it's not as simple as gravitons or the rest. But in some sense, things like what would be roughly the equivalent of gravitons are already, the quantized, linearized quantized perturbations, if you want, of the space-time metric are already playing a role in this next to 1/n. So it's just that in some communities, in some terminology, this would be going beyond already quantum field theory and curved space-time. So because you're already considering this linearized quantum gravity, if you wish, on top of that background, as opposed to just having other quantum fields, and then the space-time or the geometry, the metric, is just classical. So I know that in string theory, you don't just have the thing that would correspond to the metric, you have some other fields, and it's a combination of all those. But so this doesn't impact what you're saying. In some sense, it's actually highlighting that you're already, I think, with this probing or discussing some aspects that involve at some first level some things that have to do with quantum fluctuations of space-time at a very linearized level, if you wish, but at first correction. But maybe we can leave that for the discussion at the end of your talk. I don't want to.
Sorry, yeah. I think I see your point though, but yeah, okay. Okay. So just to recap, the point then was just that just like in this first example of how we use teleportation to replace this scattering region for a very simple task. I highlighted there that thinking about quantum information in a space-time context emphasizes that entanglement and aspects of the geometry can kind of be alternative resources for completing the same task. That's sort of made really manifest in the context of AdS CFT, in that here there's two perspectives, the bulk and boundary perspective, and those two ways of completing the task, using the geometry or using the entanglement, are sort of realized simultaneously in the two pictures, right? So in the bulk picture, we use the geometrical kind of resource, and in the boundary picture, we use entanglement to replace it. Okay, good. So let me continue to sort of discuss this second point, which is about how it is that gravitational degrees of freedom are getting written into or recorded into the conformal field theory. And we're going to be taking the same perspective, of course, where we're thinking about these quantum tasks. We're just going to take the reasoning sort of a little bit further. Okay. And in particular, the kind of chain of reasoning that I want to follow is we're going to think about some bulk task T. Okay. And we are using the existence of some causal feature in the bulk to say something about how well I can complete that task. So, for instance, before we were saying, oh, there is a scattering region, and that, seems like it makes it so we can complete the task with high probability. Okay, so we start with some causal feature, we turn that into some claim about the success probability. Then from this statement I made earlier, or this interpretation of the correspondence, that becomes some claim about the success probability in the boundary now. And then the last sort of step that we want to do is turn this statement, really about the boundary theory, but about these success probabilities, into some maybe more conventional kind of statement about the conformal field theory, or about the boundary theory. Okay. So we're going to follow that chain of reasoning for the task that we already thought about, where we have this kind of scattering scenario. I'm just redrawing that here on the right with a slightly fancier picture. So we have this scattering region J, and we're going to say that, okay, that's going to let me, implement maybe some simple unitary in the bulk. So we're going to say the success probability is large, say it's 1. That means the boundary success probability is large. And then these statements coming from the cryptographic literature, which are saying that, in order to, or sorry, let me go back a step. So this success probability is large. We know from what I was saying before that the way that this process is happening in the boundary is as one of these non-local computations. And then we know from results about non-local computation that entanglement is necessary for doing those computations, or for having that process happen. And so that gives us some statement about correlation in the boundary. Okay. And for later purposes, I could talk about various different measures of correlation, but for later purposes, it's going to be convenient to focus on the mutual information. Okay. So this success probability being large means that the mutual information is, in some sense, large. When you go into this in more detail, it turns out that the right notion of a large mutual information is a mutual information which is order 1 over g Newton, where g Newton, by g Newton, I mean the usual Newton's constant that appears in Newton's force law or Einstein's equation. Okay, so that's saying this is big. Okay, so that's good. That's sort of turning this line of reasoning into some more conventional kind of object, or translating it into some consequence for some more conventional sort of object in the CFT. To be a little bit more precise, when I say there's large correlation in the boundary, I should say large correlation between which regions. Just 1 sec, I'm just going to finish this. So in particular, it turns out the right regions to think about are these ones, V0 and V1, which are just defined by taking the for V1, say taking the future light cone of C1 and the past light cone of R1 and R0. And then for C0, look at the future light cone of C0 and the past light cone of R0 and R1. Those are the regions in the boundary field theory that should have this large correlation. Okay, yes, Albert.
Yeah, just a minor comment that might be helpful for those who are maybe less familiar with this. In terms of this AdS CFT, where you have a large number of fields in the conformal field theory, and this large that this 1 over G Newton that you say here, in terms of that, right, it would be proportional to n, right, or something like that, or n squared, depending how you measure it.
Yeah.
So,
sorry. So I phrased this in a slightly weird way because I made a statement about the CFT, but using a gravitational parameter. But yes, there's some way to reframe that.
Right.
In the
Right.
in purely CFT language, let's say, which is saying it's n squared, where n is somehow the number of sort of, you can think of there being lots of different field theory degrees of freedom in the CFT, and this is saying sort of all of those field theory degrees of freedom are correlated.
Exactly, and you recover the classical. You have the emergent classical. So it means that that's where exactly this.
Yeah, it's kind of n squared or 1 over G Newton is related to kind of the classical physics in the bulk, and this is kind of related to the fact that there's a classically there's a space-time region in the bulk classical geometry that's leading to this large correlation.
Right. Yes. Thank you.
Good. Okay. So that lets us translate from this bulk geometrical statement to a somewhat more quantitative, precise claim about the CFT. And I sort of already said this, but I'm kind of revisiting it from slightly different language to emphasize a different point, which is that one thing this is saying is that data about the bulk geometry, right, in particular the existence or non-existence of this scattering region in the bulk, is written into the CFT, or, it's recorded into the CFT, and the way it's recorded is in terms of the pattern of correlation that I see in the CFT. So this bulk metric data is written into the pattern of correlation in the boundary. Elliot.
Could you please clarify what you mean by two regions of spacetime that are strongly or weakly correlated?
So I mean, it's just saying, well, okay, so I mean, maybe I have it on the next slide, right? So the mutual information would be defined in terms of, traditionally, even in sort of finite dimensional systems, defined in terms of some linear combination of entropies. And even in a field theory, there is some way of computing, these von Neumann entropies. And in field theory, where things are infinite dimensional, a von Neumann entropy is typically a divergent quantity, or it's infinite. It turns out this mutual information is finite and is well defined in the field theory, and that's the object that I'm talking about here. Maybe that doesn't answer your question though.
Do you have an example of something that would be a weak correlation, for example?
So if you took your regions V0 and V1 to be quite small, then when I compute the mutual information, it will come out to be order 1. And that's what I'm referring to as sort of weakly correlated. And then when instead these regions are bigger and the correlation, it ends up extensive in the number of degrees of freedom that I have in the CFT, then I'm saying it's strongly correlated.
Thank you.
That helps. Okay. Good. Yes.
So maybe a follow-up question, since this was asking this. Suppose that instead of V0 and V1, this goes against what you're saying, but just to, or doesn't go against, but it's a different case. Suppose that instead of V1 and V0, as shown here, that you were considering the sort of that causal, I mean, that diamond that you have in between V0 and V1, so that it's causally disconnected, exactly. But it's the next one. So would this mutual information between the two sort of adjacent regions like that, or connected with this, be lower or higher than V0 and V1?
When I'm in the regime, so the claim I'm making is about the regime where there is a scattering region J.
Yes.
So in that case, I'm claiming this guy is big.
Yes.
V1 is big. It will actually happen, let's call them x0 and x1 or something, that those will be order 1. Yeah, this one being order n squared actually implies the other one is order 1.
So do I understand correctly that when I have two that will have a common scattering region in the future, that then the mutual information is lower for those two, though they are causally disconnected?
Yeah, these, I mean, you could, it would be a maybe less intuitive way of thinking about it, but it would actually be an equivalent statement to say that when there's a scattering region, these other regions have order 1 mutual information.
So when you say these other, it's not the two red ones, but it's the red one with the V1 that I was asking, or is that correct? Or
you want like this?
yes, but just not the whole thing, but just, you know, the two small diamonds, V1 and one of the red ones.
Oh, like I see, like this.
Yeah.
Sorry. So that so in field theory, when you're calculating an entropy, you are actually always thinking about the like the domain of dependence of a region. So if I have some, I have some field theory and I look at some interval, the entropy is always associated actually with the whole diamond. It actually doesn't make sense to ask about the entropy of this smaller thing. Basically because once I have like this slice down the middle or this interval, then causally everything inside of that diamond is determined. And so it only sort of makes sense to ask about the entropy of the whole diamond.
So somehow I thought that, especially if we talk about mutual information and so on, I mean, it's like the entanglement entropy between these two regions, right? That's something that sometimes one considers that. But then again, maybe we could leave this for the discussion afterwards. I don't want to interrupt your sort of line of presentation.
Sure.
We can come back to this point later, maybe.
It looks like there's another question.
Yeah, thanks. Maybe also a bit of a follow-up. Is this mutual information related somehow to the strength of entanglement between the two regions, or like, yeah, perhaps
it's not super clear.
Is it a quantum correlation? That's what I was wondering. Is it distinguishable somehow?
Yeah. So okay. So the reason I went to the mutual information is that we, as I'll talk about later, we know how to compute that we know how to compute that from other perspectives in AdS CFT, and that's going to let us connect this story to other stories and give more insight. And okay, we'll get there. You could have also asked, is this really, do I need correlation or am I talking about entanglement? And if I say return to this picture, then you can actually show that you do need entanglement. So you could, for instance, you use, I don't know what the right symbol is, say the relative entropy of entanglement. So I have some system A, B here. You can also show that this thing needs to be large if you, in order to complete some computation in this form, you can show there's cases where this relative entropy of entanglement needed to be large.
Right. So the mutual information is somehow maybe a necessary, but not necessarily like a sufficient condition to achieve the task. I mean, like you have other quantities to tell you more about the entanglement.
Yeah, that's right. It's just those other quantities. Yeah, so I guess
they are divergent. I guess that's one of the reasons why you want to, as you mentioned earlier, right? That if you were just considering the entanglement entropy, it would be divergent, strictly speaking.
that would be divergent. I think the relative entropy of entanglement would be convergent.
Yeah.
It's just that we don't know how to like. So this is some chain of reasoning that I'm giving, right? It's not really a proof. At least it's not a proof that my high energy theorist colleagues are going to believe. But what we're going to be able to do is like prove this statement. Once we find the statement using these sort of techniques, we're going to be able to prove it from another perspective. And that proof will rely on considering the mutual information, which is somehow a simple quantity that I have other techniques for. I think it's also true that the relative entropy of entanglement or some genuine measure of entanglement would also be large. I just don't have a separate calculation where I can go and verify that. I only have this argument. Anyway, so that's why I'm focusing on this quantity, but I think conceptually you should think about there being lots of entanglement and not just correlation between these regions.
Okay, thanks.
Okay, yes. So okay, so yeah, we have this basic lesson. Facts about the geometry, gravitational data is being written into the pattern of correlation in the CFT. But like I was hinting at in the questions, there are other perspectives on correlation in the CFT, and let's try. We're going to try and connect this perspective to those ones. Okay. So the mutual information, like I said, is some linear combination of entropies. In AdS CFT, we have another technique for computing an entropy. Okay. So this comes from a famous result known as the Ryo-Takanaki formula. The way that it works is we're going to pick some subregion of the CFT, and I'm going to draw this in a time slice. So I've taken my cylinder, I've picked some particular time that leaves me with some circle, and I'll pick some boundary region that I'm calling R, and then I'm going to ask, what is the von Neumann entropy of R? Okay, that's something I could ask for and try and compute in the CFT. According to AdS CFT, these theories are equivalent, so that means there should be some alternative way of computing this quantity from a bulk perspective, from the gravity perspective. The Ryo-Takanaki formula gives us a way of doing that. And what it says is you should look at all of the surfaces that sort of enclose R and extend through the bulk, right? So this would be a candidate surface. This would be some candidate surface. We're going to look at the area of all of those surfaces, and we're going to take the minimum, divide by 4g Newton, and it turns out that will compute the entropy for you. Okay. Good. So this is a different perspective or another way in which gravitational data is getting recorded into boundary correlation. It's a little bit different though, because now we're talking about bulk minimal surfaces, and that's going into some statement about correlation. Whereas on the previous slide or the development that we were giving, it was causally defined aspects of the bulk, some overlap of some light cones that was related to boundary correlation. Okay, and yeah, a nice thing that we can do is kind of combine these perspectives. Okay, so I explained already that if you have this scattering region in the bulk, then you have this strong correlation in the CFT between these regions V0 and V1. And then using this Ryo-Takanaki perspective or formula, we can then translate that statement about the mutual information being large into some statement about minimal surfaces, right? So mutual information is computed in terms of entropies. Entropies are computed in terms of these areas of surfaces. This statement about the mutual information means something about surfaces. I won't go through the translation, but at the end of the day, what you get is that whenever this mutual information is large, it will mean that the minimal surface that encloses the union V0 union V1 will have a certain topology. So in particular, it will sort of jointly connect V0 and V1 like this, as opposed to kind of separately connecting V0 and V1. Okay, so this one has less area than this one. Okay. And that connection goes both ways. So given this statement about the topology of the minimal surface, it also implies that the mutual information is large. Okay, good. So then we can combine the two statements or combine the two perspectives, and we find that, okay, if there's a scattering region, then there's a large mutual information, and then that means that the minimal surfaces have a particular topology. So combining these things, we end up with this claim, which is that if there's a scattering region in the bulk, then the minimal surfaces have to have this configuration. Okay. And what's nice about this is that that's a purely geometrical claim, right? So this over here was a statement about the boundary, about the CFT. But I can now sort of forget about that and just say, I've connected this aspect of the geometry, the scattering region, to this other aspect of the geometry. Okay. And because it's now just a geometrical statement, I can actually try and prove that statement directly within the theory governing the bulk geometry, which is general relativity. And indeed, we are able to do that. So assuming some standard energy condition on the bulk called the null energy condition, some sort of reasonableness claim about the geometry, and using standard tools in general relativity, in particular what's called the focusing theorem, we are able to just directly prove that if there's a scattering region, the surfaces have that topology. And that kind of validates this reasoning from this sort of operational reasoning from quantum information and quantum information in spacetime, and validates it using totally standard, trusted, known techniques. Okay. Okay. So okay, that's one thing that we get out. We get these new statements relating causal aspects of the geometry, sort of surfaces aspects of the geometry, and boundary correlation. And it comes from taking this quantum information processing tasks perspective on the correspondence. We can continue and we can keep trying to apply insights from relativistic quantum information theory to AdS CFT using the same sort of setup and the same kind of chain of reasoning. And since this original work was done, we've been doing some further examples of that. I won't explain them, but I just kind of wanted to highlight that this perspective seems to be kind of flexible and give you sort of a number of different interesting statements. Okay. Good. Okay, so I'm a little over time, so but we're wrapping up anyhow. So let me just summarize. So the first point that I wanted to make, which was just a point about quantum information with sort of causal constraints, is that geometrical features can be replaced sort of as resources with entanglement resources, and then that in holography we end up with this funny situation where the higher dimensional theory has richer or more causal features that the lower dimensional theory is lacking, and the way that these theories can nonetheless be equivalent is that the boundary theory kind of makes up the difference with by having some appropriate entanglement. Okay. Taking this approach, this kind of relativistic quantum tasks approach to AdS CFT, we also learned some new insights into how the bulk geometry, how bulk gravitational degrees of freedom are written into the boundary, and it highlights a new aspect of how bulk geometry is written into this boundary correlation. But, okay, so that's everything I want to say. Sorry for running over, and thanks.
Thank you very much for the very clear and interesting talk, Alex. Do we have any further questions from the audience? If maybe I start with one. So in the part that you presented about, so maybe let me turn on my video. So in the part you presented about the quantum position verification tasks, so you talked about the necessity of entanglement. In that literature, people also then talk a bit more on the bounds on how much entanglement would be needed to achieve, to implement a certain unitary. Are there analogous bounds on the AdS CFT side, and how do they compare? Like, is there also
yeah, it's a really interesting story that I've spent a lot of time worrying about. So in particular, in the position verification literature, or more generally in the literature on understanding these non-local computations, very, very little actually is known about, if I specify some unitary or some channel, we don't know a lot about how much entanglement you need. In certain cases, we can prove a like linear lower bound on entanglement. So for each qubit of input to the computation, you need sort of 1 EPR pair worth of entanglement. That suffices for the reasoning that I outlined. That suffices to get you this sort of order 1 over g Newton or order n squared scaling of the mutual information. And okay, that sounds, yeah, so that's fine for the story here. But then the sort of puzzling situation is that for sort of most unitaries, or most sort of not totally trivial unitaries, in terms of upper bounds, in terms of, in terms of the best protocols we have for implementing them in this non-local computation form, the entanglement cost is really huge. So it's often, say, exponential. And if it's really exponential, then this kind of picture where operations happening in the bulk are reproduced as these non-local computations, that would say, like, in the CFT, we only have so much entanglement. There's some specific amount of it. And so any unitary or any computation that requires I have more entanglement than that should somehow be forbidden from happening in the bulk perspective. So yeah, the situation is kind of like either there's much better upper bounds on entanglement in these non-local computations, or there's like very strong restrictions on what computations or what unitaries can actually happen in the bulk of the AdS space. And that's a tension that's been sitting there in the literature for quite a while. And I think it's unresolved, and resolving it comes down to better understanding non-local computation and the entanglement cost there. Yeah, so it's an interesting problem, and it's open, and it's something I think about a lot. But
okay, thanks a lot. Do we have any further questions?
I mean, from my side, there were a few things that we could discuss later. I think they became more or less clear. Perhaps the question I was trying to ask, the last one, I think that probably Pilasini was clarifying that partly with her question. So this distinction between direct measure of entanglement and mutual information, I guess that was related to the point that maybe was not clear to me. But if we try to talk about the measurements of entanglement, I'm not sure whether there are results there, not necessarily following from what you presented, but in those two different pairs of regions that we were talking about, the contiguous ones or the more separate ones, your V0, V1, what's the expectation in terms of entanglement between those two different pairs of regions, that they are substantially larger in one case or comparable? Could you elaborate on that?
Yeah, so I think the expectation in the AdS CFT literature is that those regions, V0 and V1, are entangled, not just correlated.
Yeah,
I think it's there's some evidence for that, but it's sort of hard to do a sharp computation that shows that. Yeah, and I think this is certainly a good argument that you should expect that to be the case. Yeah, I'm not sure if that totally addressed your question though.
Well, I think what you're saying is that actually these results, there are conjectures about these things, because you were talking even about the entanglement between V0 and V1, that there are conjectures or expectations about that. And I was asking the comparison between that and the case where you were comparing, the two contiguous regions, that contiguous.
Oh, yeah, so those...
But I guess again, it's well, in those you have probably, I'll let you just comment on
that. That's somewhere between fine and trivial or something. So if I think about like splitting it up this way,
yes,
then often I'll have a pure state. My CFT state could be pure. At least in the simplest situations, it would be pure. And so then I would be talking about a mutual information or some measure of correlation in a pure state. And then there's then we know the mutual information just is calculating, entanglement in that setting. On the other hand, the mutual information between two contiguous regions, will actually just be infinite. So yeah, I said the mutual information is finite, but that relies on things being separated. As I bring them together, it's gonna diverge actually.
Okay, thank you. That also clarifies, because this was a point that wasn't clear from your answer later. So yes, I see. Right.
Yeah, but it is the maybe something I didn't really emphasize is that it is these regions V0 and V1 are they are picked out by the argument that I'm giving. So they are sort of the right, well, I think they are the right regions to talk about. So in particular, if we think about this non-local computation picture and I want to compare to that, then this operation is something that can take things in from C0 and get things to R0 and R1. So from there, I should argue that this site where I'm sharing this entanglement should be identified with the portion of the bulk that's in the future of C0 and the past of, the portion of the CFT that's in the future of C0 and the past of R1 and R2. So yeah, this kind of graph.
I think that you made that point very clear. Yes. In fact, I have not been following the work in the community on these topics, but I just heard the buzzword EPR equals ER and so on. But when I was listening to your talk, I thought that this was very clearly emphasized. So I think you made very clear also why these regions are important. So I don't know. Actually, I was going, since, as I said, I've not been following this at all. So I was wondering how this, what you were presenting, that seemed very clear, very convincing to me. How does that compare to other approaches of people working on this ER equal EPR? So what are other approaches that people have been taking to kind of discuss this point that I thought was very nicely sort of shown?
Yeah. So I mean, there's a lot of interest generally in the relationship between the geometry in the bulk and entanglement in the boundary. And I would say the main other approach is this one I was discussing in terms of this Ryutaganaki formula. So this gives you, another way to think about how geometry is related to boundary entanglement. And, indeed, this perspective came before my perspective. It goes, way back to 2006. And, I'd say a lot of insight has been gained from that kind of perspective. I mean, I don't know. I mean, one prominent line of work that's been very interesting has been using this kind of perspective to explore the physics of black holes and longstanding puzzles around around, for instance, the black hole information paradox. So there's this long-standing question going back to Hawking and Page of the Page curve. So you're looking at the von Neumann entropy of all of the radiation that has come out of the black hole so far. And if the black hole is unitary, then at the end of the day, since you're holding the whole system, you need to have 0 entropy. But when you're looking at half of it or something, you could have some large entropy. So you can get some behavior that kind of comes up and then goes down. But for a long time, when you did some gravity calculation and you tried to compute this, you got something like this instead. Maybe people are familiar. So this was some puzzle. It looked like unitarity was being violated. What's going on? And now, from a long line of work and reasoning that you can see as starting really with this Ryutaganaki formula, we now know how to do a gravity calculation where this Page curve comes back down. And we understand what the error was in the previous way of doing this calculation.
So I have not been following, I've been disconnected from these things for a number of years. So could you say a few key things about just this point you're mentioning? So what's the key idea in these recent developments that when you said that now we know how to, and we understand what was the thing that we were sort of missing? Could you elaborate briefly on that if possible?
Yeah, so there's maybe 2 ways to think about this, one of which I'm not really an expert on, but so one thing we can say is we can actually use, if we build our setup right, there's a way to be using this formula, this Ryutaganaki formula, to do the calculation of what I can in some sense take this region R to be the radiation system that's escaped from the black hole. So then I can use this Ryutaganaki formula to compute the entropy for me. And this formula, or at least sort of refinements of this formula, turn out to correctly compute the entropy for me. So it computes it in a way where this comes back around, and I see this sort of signal of unitarity and that the entropy returns to 0. And okay, so that's nice, but then maybe it's a little unsatisfying because there was some other way of doing this calculation, and which one is right. But fortunately, there is also an understanding. So this formula is Ryutaganaki formula. At first, it was just conjectured. Like Ryutaganaki just noticed that these objects behave the same in a number of situations, and then conjectured that they were equal. But from there was a sequence of really important works which showed how to actually derive this formula, starting from a sort of path integral perspective. Okay, and yeah, people sort of built on that, made it more and more rigorous, or closer to rigorous. Path integral is often hard to make rigorous, but okay, they understood this pretty well. And then, by looking at that understanding of where the Ryutaganaki formula is coming from, and what about it is letting you compute this entropy curve that's coming back down, they could then see how to correct, or what was missing in Hawking's original calculation that was leading to it coming up. And yeah, basically they realized that he dropped some terms that can become large and that you shouldn't drop, and it was easy to identify those once you had this Ryutaganaki perspective. Yeah, I think that was a lot of progress on this problem.
Thanks for the overview. What could be a good reference overview to this point, and in particular these terms that you mentioned that were being sort of missed by?
Yeah, I'm forgetting the name of the paper. There was a paper by Jeff Pennington where he's just using some modern version of the Ryutaganaki formula, some updated version of it, to do this page curve calculation. And then there's a follow-up, and I should say actually at the same time, like same release day, there's a sort of companion paper or maybe competing paper from a number of people on the East Coast at IAS, Juan Maltesina and a few people who do a similar calculation, come to a similar conclusion in a slightly different model. And maybe the difference is that they're in like more of a toy model, but can do a more rigorous calculation. And then Jeff is in, a more realistic situation, but does a slightly less rigorous calculation. So okay, there's those two perspectives on it. And then there's a follow-up, again, from the two sort of competing groups or collaborating groups, where they both kind of identify in the path integral calculation what was going wrong and what's going on under the hood from this Ryu-Takanaki kind of perspective. And that paper I would have to check the name of, but that's where they're pointing out,
These things that are missing, I always had a little bit impression based on some partial results that people had that something that would probably play an important role is that whereas the traditional calculations arguments were really based on having small fluctuations on top of a given background of the evaporating black hole, that somehow there were contributions maybe with small amplitudes, but whatever, from very different geometries that were also fluctuations around very different geometries. So these contributions that are missing there, can one kind of interpret them as a little bit related or in that sense, or? Yeah,
that's right. Yeah, there's just terms that you thought were small, but yeah, basically the dominant saddle in some path integral like flips at some point to a different geometry, and that was missed initially, but yeah, now it's been identified, and that change in the saddle leads to is where this like turnaround comes from.
Thanks a lot for the overview and the summary.
Yeah, so I think we're coming to the end of the prescribed time, so I can leave this channel open if people still want to discuss, but maybe we can stop the recording and stop the official part of the seminar, if that's okay.
Yeah.
Okay, so yeah, thank you again for the nice talk and the discussion. So let's
thanks for the invite.
stop here.